Very good afternoon to all of you. So in the previous sessions, we have discussed about the AC fundamentals. So AC fundamentals and along with the sine wave generation. Okay, so simple loop generator. From that one we have derived that the simple loop generator. Okay, how sine wave is generator for AC. Okay, that we have discussed. And now we will see the practical. Okay, so in the animation we are see the today class. So how sine wave jet for 90 degrees, 180 degrees, 270 degrees, 360 degrees. Okay, so how it's generated. Let's see the today lecture. So they have discussed the alternating current. So why it is called the alternating current cycle. Okay, so and also angular velocity waveforms. So we have already discussed. So just we'll go to the today lecture. So simple loop generator also there. Okay, let's see it. Okay, so here, so today lecture start with the animation. One simple loop generator. Okay, so simple loop generator is the consists of the single turn rectangular copper coil. Okay, and place in between the poles of the magnet. Okay, in place between the poles of the magnet and used to study the EMF. Okay, how voltage is generated. Okay, so here you can see this slip rings and here is the brushes. Okay, so in the practical generator also same will be there. Okay, so but some construction will be different, but the operation, okay, which is running operation, that will be same. Okay, let's see. So here having the positions. So 0 position, 90 degree position, 180 position, 270 position, 360. Okay, you can observe. So here in this position. Okay, so 0, 90. So how is the 0 position and 90 degrees position? Okay, so how it is be work. So let's see. Okay, in the animation. Okay, so here is the land. So north pole and south pole. Okay, so here is the these are the slip rings. So slip rings which are connected with the brush, and here is the rest. So here is the we are placed the that is the wire. Okay, so copper coil we are placed. So here you can see A, B, C, D. Okay, the ends A, B, C, D are there. Okay, so observe that A, B, C are the ends, and here S1, S2, okay, resistor, and north pole to south pole is placed. Okay, so here is the it will be the flux. Okay, flux is from the north pole to south pole. The flux is flowing from north pole to south pole, and here the it placed the winding. Okay, that's a coil is placed. So let's so when current is flowing. Okay, so when 0 degrees, so we are at the 0 degrees. Okay, so at 0 degrees the induced EMF, that is the 0. So these arrow directions flows that the current direction. Okay, the current direction in the coil. Let's take. So here you can see when the rotations take places, okay, from 0 degrees to 90 degrees. So current is flowing through this. Okay, 0 degrees to 90 degrees, the current is flowing. That is the uh, from the Faraday's law. So whenever the conductor cuts the magnetic field, some EMF is induced. The induced EMF you can see here. Okay, so induced will gradually increase to zeros to okay magnet, some magnet. Okay, at the 90 degrees it is the maximum, and here from 90 degrees to 180 degrees. Okay, so it is gradually decreasing. Okay, you can see the directions of the current in the magnitude, so it's gradually decreasing. That is the magnetic flux is produced, that will be reducing. Okay, and here from 180, okay, at 180 it is a 0, but it's because there is no flux cutted by the conductor. Okay, so there is no EMF there. So from 180 to 270, there is a reversely current flow because the direction of the current which is the reverse. Okay, that's why it is the showing the 0. Okay, in the negatively it is the magnetic value. Okay, so here next from 270 to 360. Okay, it's again increasing. Okay, so it's again increasing towards the positive side. That's the magnetic flux cutted by the conductor is increasing. That's why it's the value is increasing. So this is the how is the EMF generator. Okay, in the okay this generation for this sine wave, okay, this is the sine wave. So in the DC generation, okay, so the DC generator is have we need the only the pure sine. Okay, so in the DC, okay, this is for the AC. Okay, in the DC generator, okay, so we have discussed that is a single loop DC generator set. So for DC, okay, so we are using the split rings. So the split rings we are used, okay, so instead of split rings we have placed the, that is the commutator. Okay, instead of that, so we have placed the commutator. So this commutator what will do, that is at the end side. Okay, so before that it will be a sine wave, but at the here instead of the this split rings we are placed the another sum. Okay, so commutator place, this commutator what will do, so it will converts the AC to DC. Okay, alternating quantity to DC. Okay, so that from first it will be stays the half wave output. Okay, then it will continuously pure term. Okay, if number of conductors if increase, okay, so this is for the single current. If number of conductors increases, the magnitude of the DC, that will be the pure light. Okay, that will be pure magnitude. Okay, without they having the frequency compensation. That is it will convert, that is a AC to DC by using of the commutator. Okay, in the DC generator. In the AC generator, that is a sine wave only. Okay, so you can see, okay, 0 degrees how it will place, and 0 to 90 degrees you can see. So when the 90 degrees fly, okay, 0 to 90 degree angle, so the direction, okay, induced EMF direction you can observe. Okay, so 180 to 270 degrees you can observe. So 270 to 360, so you can see. Okay, so animation, because show the animation which is the understanding purpose. So here's the EMF gyres. This one is shows the current flowing. Which direction is current flowing is the for this one. Okay. So this is the simple. So yeah, no the how EMF generator from the simple. Okay, why we are taking the sine wave as representing the AC quantities. Okay. So let's see talk about the, so we'll not need these precious slip rings. Okay, so just we'll go to the today lecture. So already okay, now we'll talk about instantaneous value, maximum value, frequency, time period. Okay, average value, RMS value, form factor, peak factor. So these are the some definitions we have. So it will come to the questions. So while understanding, so instantaneous value, maximum value, frequency, time period, average value, RMS value, form factor. So some of the quantities were will have to know about the AC quantities. Okay, we have to know the some quantity. Okay, some definition we have to must know some topics. So let's start. So here instantaneous value. Okay, so the magnitude. Okay, so instantaneous value, the magnitude of the alternating quantity at any instant is known as the instantaneous value of the alternating quantity. Okay, the magnitude of the an alternating quantity at any instant is known as the instantaneous value of the alternating quantity. Okay, so here we can see, so in this, so here is the sine wave there. So at the magnitude, okay, here is the 10 volts magnitude positive, in the 10 is the negative. Okay, so these are the different. So this is the one instant value, this is another instant value, this is a 90 degrees instantaneous value, here is the 180 degrees here. Okay, so these are the different. The magnitude of the any alternate quantity at any instant is known as the instantaneous value of the alternating quantity. Okay, next is the maximum value or amplitude. So here see the maximum value of the positive or negative of any alternating quantity. Okay, of alternating quantity is called as amplitude or peak value or maximal. So you can see in this one. So this is the a, if you observe this sine wave. So this is the maximum value. Okay, so this is the lower value. So at this one is called as amplitude, or it one called as a peak value of the this sine wave. Okay, so next frequency. So frequency is nothing but number of cycle. Okay, the number of cycles completed by an alternating quantity in 1 second. Okay, the number of cycles completed by the alternate quantity in 1 second is called as a frequency. Okay, F is equal to 1 by T. So inverse of time. So unit is called cycles per second. That are hertz. You can indicate with the H. So Hz. Okay, so units are the hertz. So next the time period. So time taken by an alternating quantity is to complete one cycle is called the time period. Okay, so he can see the time period will be indicate. Okay, so if the one full cycle, okay, so if the one full cycle is there, okay, so this is the one cycle. So this is the positive half cycle, this is the negative half cycle. So this is a quarter half cycle. Okay, so average value. So average value is defined as the steady current. Okay, so average value it is defined as the steady current at which flowing through the given circuit or given time produce the same amount of charge as produced by the alternate current. Okay, so average value is nothing but, so this is the sum. Okay, so in the normal average what it said, so that is also here. Okay, so it is defined as the steady current which when flowing through a given circuit for a given time period produce the same amount of charge, okay, as produced by the alternating current, okay, flowing through the same current to the same time. Okay, so this is the average value. So next, root mean square value. So RMS value, so it is defined as the steady current which when the flowing through the when given circuit is a given time produces the same amount of heat is produced by the alternate current when flowing through the same circuit for the same. Okay, so one thing remember. So average value is different, RMS value is different. Okay, so if the RMS value is okay, so there will be different. Okay, so average value is different, RMS values are some difference with them. Okay, so if we take, so here is the 220 volts DC supply. Okay, that is the average value. But when come to the 230 volts AC supply, so it will be different for which is the RMS value or it may be our average value. Okay, so we have to just be confused. Okay, so we have to know that always the value which is given, okay, we have to know either average value or RMS value. Okay, so defined as the steady current which when flowing through any given circuit for a given time produces the same amount of heat produced by an alternating current, okay, when flowing through the same current for the same time. That is the root mean square value. Okay, so effective value or virtual value. So the 230 volts AC in the for domestic application, that is the RMS value. So form factor. So it is the ratio of the RMS value to the average value of an alternating quantity. So form factor is nothing but ratio of, okay, so ratio of RMS value, RMS average value is called as the form factor. So next, peak factor. So peak factor is nothing, it is the ratio of maximum value to the RMS value. Okay, so maximum value to the RMS value is called as the peak factor. Next, average value. So already discuss. Okay, so methods of calculating RMS and average values are alternating. Okay, let's see. So which method? Okay, so we don't know it. Just we'll go to the methods. There's a bit oriented method, bit ordinate method, analytical methods. There are methods of calculating average value. Okay, so here is the different instance values are there. Okay, for the time period with some time along with the current. Okay, so for instance times are there. So here the I1, I2, I3, I4 the also. Okay, so here is the I n different values. Okay, with the time period 1 say. So here dividing the time with the into the equal intervals. Okay, divide the time base into the n equal intervals of time. Okay, equally dividing the interval time, and each time duration is t by n second. Okay, here each time duration is t by n seconds. So let the magnitude of the instantaneous current, that is I1, I2, I3, in the regular intervals. Okay, then the average value of the alternate current is given by the average is equal to I1, I2, I3 plus by In by n. Okay, similarly in the mathematical the average value is calculated. Similarly here also. Okay, so sum by total. So total number of, okay, that is the aim. So next here the mid ordinate method for RMS value. So here we can see the instantaneous values of time, and here dividing the t equals the number of time and t by n seconds. So let the magnitude of the instantaneous, that is I1, I2, I3 regular time, and I with the alternate quantity passed to the resistor. Okay, so here is the we are considering the resistor because here heat. Okay, how much heat is produced, that is we are called. Okay, that's why we are taking the here heat. So here heat is we are considering. So heat I is the alternate passed through resistance of the ohm. So then the heat is produced because in the resistor. Okay, so the power is flows through the, okay, so the resistor is there. Okay, so what will happen if the current is flowing means it will opposing the flow of current, but the opposing flow of current, okay, is the changes to the current is producing the form of the heat. Okay, so the alternate current passes to the resistor R ohms, then the heat produces the first interval. Okay, so 0.24 I1 square by RT by N square. Okay, so the mathematical calculation second interval, so some seconds will be there. So n intervals 0.24. Okay, so these calculations the standard calculations, so don't think that so how much it's there. Okay, just forward that. Okay, standard. So total heat, so here is a pose, here is the heat is produced by this one. Okay, 0.24 resistors. Okay, number of resistors there, and the suppose a direct current of the value I produce the same heat with the same resistor during the same time. Okay, suppose a direct current of the value I produces, okay, current produce the same heat to the same resistor during the same. So here at the AC we are coming. So similarly if DC, okay, same amount of DC current and same time if resistors flows, okay, it heat is produced, that is a 0.25 I square RT. Okay, that's the current. So here by getting the equations we'll get the IRMS. Okay, so from these equations, okay, we, because here we are equally maintaining, that is we are placing, that is heat, the amount of values which is produced heat is the equating the DC and AC. Okay, from that one we are taking the I value. IRMS equal to under root of I square 1 I square 2 and to the In square by n. Okay, that is a, so we can see the IRMS is equal to average value. Okay, so root mean square values can get. So here the formulas, some problems are there, so you can do uh, just give for the examinations purpose, so you can, let's see the, okay, so next we'll see the phase. Okay, so what do you mean by phase, what is mean by phase difference? So you can see in the AC quantities, so we can observe that we are having the single phase system, two phase system, three phase system. Okay, like that. Though here the what is meant by phase. Okay, so in the single phase is what is meant by phase. So three phase system, what we, so in the single phase we can say the positive and the negative values are there. In the three phase we are having the R phase, Y phase and the B phase, etc. Okay, in the positive and the negative is there. Okay, so like that. So it what, okay, so here we know the detail about the what is meant by phase, what is my phase different. Okay, let's start. So phase is nothing but, so it is an angular measurement. Okay, so it is an angular measurement that specifies the position of the alternate quantity. Okay, so it is angular measurement that specifies the position of the alternating quantity related to the reference. Okay, so here we are considering the one sinusoidal waveform. So here is the one reference. Okay, and here is the sine wave. So is the positives and negatives. So here is a 0, 5, 2, 5. Okay, 0 to 180, 180 to 360. That is a full one cycle we have taken. Okay, So here is the total time period. Okay, so t equal to wt omega angular momentum. Okay, the equation shows the waveform, that is the v equal to vm. Okay, this waveform shows the v is equal to vm sin theta. So at 0, so at theta is equal to 0, okay, at this position, so v is equal to 0. Okay, theta is equal to 0, the voltage value is 0. Okay, so when theta is equal to 5 by 2, okay, so you can see at the 5 by 2 value, okay, this is the 5 by 2 value. Okay, it is having the maximum, that is the v is equal to maximum at a given instant. Theta is the phase. Okay, so at a given instance, theta is the phase or state of the wave, can be known as the with respect to the reference. Okay, here is the reference. Okay, let's when sine wave is the shift left or right. Okay, so when the sine wave is shifted left or right with respect to the reference valve. Okay, let's check. So if the moves of some value, okay, so here is the from 0 to next. So if the goes to the uh, left or right side, okay, so at some values, so let's check. So what will happen? Okay, so here the values, so we can check the values. Okay, it is a 0, so v is equal to 0, it's change. Okay, so here is the v is equal to 0 is value from 0, theta is equal to 0, that is change, that is the theta is equal to minus 5. Okay, it goes to the minus value. So here is the positive values are there. Okay, so here's a v, the maximum value at the peak value. Okay, vm sine omega. Okay, vm sine theta plus. Okay, so theta plus 5, the angle we are placing, that is the, here we are placing is the 5 values and here placing the theta. Okay, at this point, so it is the, we can say vm sine, we can say theta plus 5. Okay, here is the same, so it is a value. Okay, so in the difference, so that will be different. Okay, so here you can see the sine vm sine theta minus 5. Okay, that is a 0 values. Okay, so negatively positive, that will be different. Okay, let's check. So direction of flux. Okay, so here is the direction of current. So direction of flux and the coil that will form. So when above system rotated, okay, when the above system is rotated in the magnetic field, the alpha, okay, is the angle in between the two current. Okay, so alpha is the electrical phase angle difference. So we are referring that the alpha, okay, alpha is the electrical phase angle difference. Okay, so emf is induced in a coil and coil b. Okay, so this is the phase difference. So you can say, so equation emf induced in the coil a, v is equal to va is equal to vm sin theta. Okay, with the reference equation for emf difference vm sin. So let's see, okay, how phase difference. Okay, so how it is a phase difference for va and vb. So here's the, you're taken sin theta plus alpha. Let's see the phase difference. So is the Vm sin omega t. Okay, so another for Vm sin theta plus phi. So you can see. So this is for the difference. You can say this is called as a phase difference. Okay, so the angle in between the two phases. So this is the one phase, this is the another phase. Okay, so the angle which is different, that is the phase different. Indicate the phi. So Va, here is the Vb, and Va is the reference. Okay, here we are taking the Va is a reference. So here's the Vb. So you can observe. So this one is the angle. Okay, the displacement is called as a phase difference. So this displacement is called as a phase difference between the angle. So next we will talk about the vector. So vector is a physical quantity which has a both magnitude and direction. Okay, so vector is a physical quantity which having the magnitude and direction. So let's see the graphical representation of the current and okay. So in the graphical representation, okay, so here is the current and voltage. So here is the, we are taking the current representation here. I of t is equal to Im sin omega t. Okay, so if graphical representation, we can say I is equal to Im maximum. Okay, Im is maximum current. Okay, at sine omega t. Okay, so here is the 0 to 2,5. Okay, the value stays with the 0 to 2,5. At the 5/2, 3/5/2, the angle. Okay, the positive at the positive and the negative flow. Okay, so here what will happen? So it will be having the high maximum. So let's check. So I of t is the maximum value. Okay, so this was the one full cycle. There is the t is equal to 1 by f. Okay, so here we can see 45, 90, 135, 180, 225, 270, 350, 369. So here is the current. Okay, so current in terms of the amps. Okay, so here you can see, so from 0 to 1, it's the maximum showing the 90 degrees. Okay, similarly at the 180 degree. Okay, so the 5 is nothing but 180 degree. So it will having the 0. Okay, so suddenly it decreasing. So from 0 to 5/2, its value is increasing. From 5/2 5, the value is decreasing. Okay, so 5 to 5, 5 3 5, that is the 270 degrees, the angle is decreasing, but the current direction is a reverse flow. Okay, the current is increasing but in the reverse flow. Okay, so from 270 to 360, the value is gradually increased to the positive side. Okay, so here is the this is a vector method. Okay, so vector method is preferred to over graphical method. Okay, so preferred over a graphical method because vector method greatly simplify the problem in a AC circuit. So so in the coming classes, okay, so we are going for the voltage and current circuits, right? So at that time, so we having the phase difference, phase displacement. Okay, so in phase, out of phase, so that will be all are represented in the waveforms. Okay, so vector waveform only here. So here you can see the voltage and current. So in this, okay, here is the phase, some phase difference is there. Okay, so it is the in phase. So this type of okay, resistive, so it is called as the in phase. So you can say that is both are start with the 0 and having the less value at the 180 and peak value is the 270 and it will having the max 0 at the 36. So that is called the in phase. Okay, so here is the waveform. So it's the vector form. So current vector and voltage vector in phase. Okay, so at this end these are both having the in phase. So you can see so direction. So it in case so voltage and current are in the in phase in a resistive circuit. Okay, so this is the for the current flowing in the resistor having the in phase. Now we'll talk about the relationship between the voltage and current in the pure resistor. So we'll talk about now pure resistor circuit, how it will there. Okay, for pure inductive circuit, capacitive circuit. Okay, that we are going to discuss. Let's check pure resistive circuit. So we're having the AC source. Okay, and current is flowing through the resistor. So at that time, so let's apply the voltage given by the equation Vm sin omega. Okay, so we are considering Vm sin omega t theta value. Okay, so that is equal to omega t, and the R is the ohmic resistance, I is the instantaneous current. So the drop across the resistor, that is the IR. So let's take the keeping the values. Okay, so Vm sin omega t, okay, is equal to R, that is the voltage in the between same is right. I is equal to I Vm sin omega t by R. Okay, so that we have here what we are taken the value. Okay, voltage value that we have. So let's when sin omega t, okay, is equal to 1, then I is equal to, okay, when sin omega t is 1, when sin omega t is 1, then the I value is equal to Vm by R. Okay, here is the current is the maximum current. Okay, here I is the maximum current when sin omega t is a 1. Okay, so we can say that here when current is maximum, when the sin omega t is equal to 1. So here, so maximum current that Im is equal to Vm by R. So when is the maximum current flow? So maximum voltage by resistor. So substituting the values, so we'll get I is equal to Im sin omega t. Okay. So for pure resistive circuit, the voltage is equal to Vm sin omega t. Then I is equal to Im sin omega t. Okay. So for pure resistor vector representation, this is the vector representation. Okay, so this is called as a in phase. So next, the power in RL. So resistor and inductor. Let's say the resistor will having, so and inductor. If you combine the both, okay, resistor and inductor. So if you combine resistor and inductor, is called as the RL circuit. Okay, so this is called as a RL circuit. If you place the another in between the capacitor, there is a RLC circuit. Okay, so only RC means only will having the, that is, so if you only having the resistor and capacitor, we can say that is the here only if you having the resistor and capacitor, it's called as a RC circuit. Okay, if it is having the inductor, so we can say that that is the RL circuit. So that is the RL circuit. Okay, RL, RC, RLC. So let's talk about the power in RL series circuit. Okay, so for instantaneous values, so P is equal to VI. So power is equal to, okay, so power in the circuit, that is the V into, so voltage and current is called as the power. Okay, so Vm Im sin omega t. Okay, so combining the 2 omega t will get, so Vm sin minus 1. Okay, so we are simplify that 1 minus cos 2 omega t. Okay, so taking the multiplying with, okay, Vm Im into 1, okay, minus 2. Okay, so we'll get the from values. Okay, first part is called for the, so for the first part is called as the constant value. Okay, so here one is for the uh, constant, another by having the real. Okay, so constant and another is the fluctuating part. So that is the, it will be variable part and the constant part. So the Vm Im is the constant, but cos omega, that will be vary with the angle, that is well as the fluctuating part. So it is a depend upon the frequency. So is the, this part, second part is a deal with the frequency. So depends upon the frequency of the voltage or current wave. Okay, so for completing the cycle, cos omega is the 0. So therefore the power for the whole cycle, that is the for total for 1 second. So we have 60 hertz there, 50 hertz there. Okay, for 50 hertz of cycle, so we'll take the P is equal to Vm Im by 2. Okay, so Vm by root 2, Vim by root 2. Okay, so then the power is equal to V, P is equal to VI watts. Okay, power is equal to VI watts. So when V and I are the RMS values of the voltage. Okay, so in the pure resistor circuit, the power in the whole cycle is never zero. Okay, so one thing remember, when the pure resistor circuit, okay, so the pure, that is a, there is no heat losses in the resistor network, then the power in the cycle is never zero. Okay, so next some problem we have in the RL cell. Okay, so we have in the, so we will have in the sum uh, that is a R and supply voltage. Okay, so we have to find out the uh, power consumption. Okay, what is by how much power consumed and how much voltage and current is flowing through. Okay, so this is a problem for you. So there are also solution is also there. Okay, just solve yourself. Okay, so next we'll talk about the pure resistive circuit. Okay, so pure inductive circuit, how much flow. Okay, so in the further class we will discuss about the pure inductive circuit. Okay, so pure resistive, how is the current flow there. Okay, so this is about the today class. So we will discuss the AC quantities and the RL circuit and how current is flowing in the pure resistive network and RL circuit. Okay, that we have discussed. Just go through the these PPT slides, then learn the, write your own notes and try to do the problems from the ebook which I've shared with you. Okay, students, this is about today class.